everyone, my name is Allison, and the paper that we're going to introduce today is the Truly Proximal Policy Optimization. Proposed in 2020, published to the Uncertainty in Artificial Intelligence. We know that PPO has a wide range of use, including the famous ChatGPT, while this paper aims to answer two questions that are often asked when analyzing the PPO algorithm, which is, could PPO bound the likelihood ratio within the clipping range as it attempts to do, which means that once we're updating the policy that is out of the clipping range, could the clipping function in PPO stop it being updating out towards the clipping range? Second, could PPO enforce a well-defined trust region constraint? By well-defined trust region constraint, we mean that the KL divergence is smaller than a certain delta. From theoretical analysis, we proved that the answer to both questions were no. So we performed the following modifications to the original PPO algorithm to fit the question that being asked. And there are three algorithms that we're going to propose. Number one, which is the PPO rollback that I'm going to tell you earlier, is to fix question number one. Could PPO bound the likelihood ratio within the clipping range? So what we're trying to do is, if it is out of the clipping range, then we restore it. So by replacing the clipping function with a penalty function, combining KL divergence. That is, if the current objective is to be clipped, then which is the clipping condition is satisfied, then we subtract an amount of alpha times the KL divergence to the original objective. The second is replace the clipping condition with the KL divergence, and if it is exceeding the trust region, so what I'm trying to say is if this is our trust region, TR, and we're currently here, which is out of the trust region. This is condition number A, and we are keep modifying the policy away from the trust region. So maybe the gradient of the objective is like this. This is condition number B. So if both A and B are satisfied, then we clip it. Here are some basic notations that you might need further in this 10 or 20 minutes, and I suggest that you could take a screenshot for further reference. Some things that I would like to highlight right now is the likelihood ratio notation, since it is going to appear so many times. And another thing is the KL divergence. So I suffer personally a lot from not knowing the exact meaning of KL divergence. Thus, I would like to talk about it now. So given an incident X and two probability distributions P and Q, the amount of information X is carrying in probability distribution P is minus log Px, which can also be written as log 1 over Px. And the entropy in probability distribution P is the expectation of the amount of information through the entire probability distribution. The cross entropy across two probability distributions is simply taking, when we're taking the probability from distribution P, we're trying to take the amount of information from the other probability distribution. So the KL divergence is simply the cross entropy minus the entropy. So let's review the trust region policy optimization. Again, I'm not going to go too deep into the proof of this algorithm because it was proved in class. For further details, please refer to the original paper also proposed by Skolman in 2015. So here are some important things about TRPO. The first one, the trust region constraint, the maximum of taking all states into consideration. The KL divergence is smaller than a certain delta. And another really important thing about the TRPO is that it is theoretically justified that it will ensure policy performance, which means that if eta pi is lower bounded, eta pi is our policy performance function we have denoted earlier. Maximizing the bound, maximizing this lower bound, would guarantee monotonic improvement on policy at each step, and thoroughly, it will ensure policy performance. So theorem number 1 is just proving this point, and let's describe TRPO formally as maximizing the objective using policy gradient, but within the clip range. And let's review PPO clip again. So the PPO clip will introduce the clipping function, f clip taking in the likelihood ratio, and epsilon is our clip range. So if the likelihood ratio exceeds the clip range, then we simply replace the likelihood ratio with the margin value. So the first one, equation number 3, is the basic definition of PPO clip. So it is taking the min of the likelihood ratio times the advantage, and if it is out of the clip range, then we simply replace it with the margin value. Equation number 4 is plugging in the clipping function into the objective, and let's take it this way. So we know that when taking the gradient of the objective, constant does not affect the gradient at all. So if we're trying to look at it in a gradient perspective, then we can simply say that if it is exceeding the clipping range, then it is simply a constant at the likelihood ratio, and we don't care whatever value it is. So here comes question number 1 finally. Could PPO bound the likelihood ratio within the clipping range as it attempts to do? The answer is no, and we're going to prove it by theorem number 2 to formally say that this is not true. So let's read through theorem number 2 together. Given the policy, which the likelihood ratios satisfy the clipping condition, let the gradients denotation and the likelihood denotes, beta being the step size, and this is the one-step updated policy. If we have the gradient dot, the gradient of the likelihood ratio times the advantage being greater than 0, then for some beta bar such that for all beta in this range, the likelihood ratio exceeding the original policy, which let's take it in this way. If it is out of the clipping range in the first place at theta 0, then if it satisfies this condition, then the clipping function does nothing. Even if it is clipped, it will keep modifying the policy away from the trust region. So this is exceeding the trust region, and it's exceeding even more. So let's get to the detailed proof. Consider phi beta as the likelihood ratio that the policy has been updated with one step. Taking the gradient of phi beta with respect to beta using chain rule, we have the dot product of the gradient of L and the gradient of R. So by equation number 6, which is the original, I'm sorry about that, which is the original condition that has satisfied, then if we have the likelihood ratio being out of the clip range in the direction that is greater than 1 plus epsilon and the advantage being greater than 0, then we know from here, since this is positive and the entire thing is positive, then we can ensure that this is positive. Thus, the gradient of phi beta at 0 is positive. This means that it is non-decreasing near 0, which means that any value that is greater than 0 but not too great to be greater than 0 would keep increasing. So for some beta bars such that for all beta within this range, phi beta would be greater than phi 0. We know that because it is non-decreasing function. So the likelihood ratio would be greater than the original likelihood ratio, and since it is out of the clip range in the first place, it is exceeding the clip range even more. And this could also be justified by the condition that the likelihood ratio is smaller than 1 minus epsilon, which is also out of the clip range, and the advantage function being smaller than 0. So it would add a minus sign to all things, but could result in the same results. So, formally, let's answer this question. Could PPO bound the likelihood ratio within the clip range as it attempts to do? No, PPO clipping cannot bound the likelihood ratio because clipping cannot remove the incentive of updating the policy further from the clip range under the condition that when the gradient of the objective dot, the gradient of the likelihood ratio times the advantage is greater than 0. So let's introduce the second question. Could PPO enforce a well-defined trust region constraint? Now we can simply by intuition say that if RT theta 0 is unbounded, then we can easily infer that the KL divergence is also unbounded. This is clearly intuitive. But if RT is bounded, does it infer that KL divergence is bounded? Well, I'm going to tell you no, that it is not true. Because now the reason why I'm saying this, talking about this point is because in PPO clip, we're trying to bound the difference of the policies that has been updated and has not been updated by clipping the likelihood ratio. And so by clipping, we want to know that if it could define a well-defined trust region constraint, which in TRPO we proved that a well-defined trust region constraint could ensure policy improvement monotonically. Here's our theorem for proving that it is not true. Assume for a discrete action space A, which the number of actions is greater than 3, let theta be the actions that are within the clip range. Then we are trying to construct a policy which, after it being updated for one step, the KL divergence between before it was updated and after it was updated is infinity, which is unbounded. So for case number 1, discrete action space, we can simply plug in the definition of KL divergence from the previous basic notation page, which we can construct a new probability distribution that satisfies that there exists an action A plus, which the probability action in the new policy is 0, but its old probability is greater than 0, meaning that this action may have a negative advantage. So we're trying to lower its probability of appearing. And this happened quite a lot because from this paper we know that it happens at a range of 25% to 40%. It is also within the clip range. Thus we have, since this one goes to 0, we have positive infinity right here. So in discrete action space, the likelihood ratio is bounded, but the KL divergence could still be diverging. Now, for the continuous action space, we simply plug in the normal distribution probability function. And if you want to know about detailed proof or detailed calculation, you could always go online. So the problem could be from this one, could be simplified to this function right here, such that it satisfies the likelihood clipping range. So for any new standard deviation that was smaller than the old standard deviation, the maximum value would always be greater than the old distribution. So let's take it in this way. Suppose we have two probability distributions. This is the new one. This is the old one. And the old one looks like this. Sorry for my bad drawing. And so if the standard deviation of the new distribution is smaller, but remains the same mean, then we can have, it would simply go to the middle. So it would be higher, like this. There always exists an action which its new probability is equal to the old probability by intuition, and thus the KL divergence is also goes to positive infinity. So also for continuous action space, even if the likelihood ratio is bounded, the KL divergence is unbounded. So formally combining case number 1 and case number 2, we can answer the question that it is, even if the likelihood ratio is bounded, the KL divergence is unbounded. So the PPO rollback can effectively bound the likelihood ratio, fixing question number 3.3. And let's introduce the rollback function. The alpha right here is the rollback force, which it will roll back the function, the objective, when it is out of the clipping range. Now, since this one may not be so obvious, I rewrote the function in the following form. So we can say that if the likelihood ratio is smaller than 1 minus epsilon, so this here would be the delta, the amount of distance that it is away from the trust region, the clipping range, I'm sorry. And this is the force. So we're trying to move it backwards inside the clipping range. And this also holds if the likelihood ratio is greater than 1 plus epsilon. So now we need to prove that the rollback function can bound the likelihood ratio more effectively than the original clipping method. Given the parameter theta 0 and the step size beta, let's consider the one-step optimized policy for using the clipping objective and the rollback objective. The set of indices of sample that satisfy the clipping condition are collected in a set delta, not sigma, I'm sorry. And they all satisfy the condition that the likelihood ratio times the advantage is greater than the old likelihood ratio times the advantage. All of those indices within the set sigma and RT satisfy the dot product of any two times the advantage product is greater than 0. So for some beta bar such that beta within this range, we have the rollback function being closer to the clip range than the original clipping method. Let's consider phi beta, which is the likelihood ratio of rollback, one-step updated policy using the rollback function, minus the likelihood ratio using the objective using the clipping method after one-step update, which we can be simplifying this term into RT theta 1 rollback minus RT theta 1 clip. Now it's easier for you to tell. And also taking the derivative using chain rule, we have the gradient of the objective of the likelihood ratio is simply the partial derivative with regard to theta 0. And this one is taking the derivative of this two and minus them together. So since the indices are out of the clipping range, which means that the likelihood ratio is simply a constant right here, we can know that this term has been diminished. So let's put an X right there. And by the rollback function previously, we can derive that the minus alpha is the pole force, the rollback force, while this one gives all of the definitions for the entire rollback function. So for case number 1, let's consider the case that the likelihood ratio is greater than 1 plus epsilon, and the advantage is positive. Then we have this one is positive in case number 1, so we know that this one must be positive. So this whole term is smaller than 0. Being smaller than 0, meaning that it is non-increasing. So for beta with beta bar such that beta within this range, any small pubescence that's greater than 0 is smaller than the original value, because this implies that it is non-increasing. Thus, the rollback function of the likelihood ratio of the rollback function is smaller than the likelihood ratio using the clipping objective. Thus, it is effectively pulling it back into the clip range. Now for case number 2, which the advantage is smaller than 0, then we know that this is negative. And plus the negative sign right here, this one is positive. So this is non-decreasing. And so for beta within the range, any pubescence is greater than the original value because non-decreasing. So the rollback function is also smaller, thus also pulls the likelihood ratio back. The ability of pulling it back is greater than the original clipping function used in PPO. Now we have to prove that PPO rollback can actually limit it within the clip range, meaning that the rollback objective will not exceed the clip range as a result. So let pi nu be the pi that could maximize the rollback objective. If alpha goes to infinity for all state action pairs, the likelihood ratio is within the clip range. So let's plug the clipping function in, not the clipping, rollback function into the objective. Now we obtain the new objective that we want, and easier for proving. So we're going to prove by counterpositive. Given an optimal policy pi star, assume that there exists a state action pair that satisfy the likelihood ratio of this certain state action pair being out of the clip range. There are 4 cases since there are only 2 options, and 2 options each being positive or negative. So let's just look at the first 2 because the third and fourth are just similar to the first and second. For advantage greater than 0, the likelihood ratio being greater than 1 plus epsilon, which we are right here. The objective of pi star is minus infinity because alpha is minus negative infinity. So it is, of course, is smaller than the old policy objective. And the second condition, which was not here, but we can derive it from the objective function. So it is not satisfying any of these conditions. It will just follow this one. And since it is out of the clip range, so we will clip it because it is out of the clip range. So we will not use the rollback to it, but use the clipping instead. 1 minus epsilon is, of course, 1 minus epsilon is smaller than 1. So it is also smaller than the original advantage. So we can now construct another policy, pi plus. If there is an action in the action space such that it is out of the clipping range, then we use the old policy. Otherwise, we use the new policy, which it will lower the value of the objective function, which is contradicting with pi star being optimal. Because if it is optimal, then there are no objective that could be smaller than the objective of pi star. So prove by counterpositive that if pi star is optimal, then there will be no likelihood ratio of any state action pair that is greater than the clipping range. So now let's get to the second algorithm. By theorem number 1, we know that bounding out divergence indicates performance guarantee. Thus, we can substitute the clipping condition with the trust region constraint, or we can say we are combining the two and taking the advantage of the two. The clipping function which employing the trust region constraint, let's stay with the original likelihood ratio if it is out of the trust region. Otherwise, stay with the current likelihood ratio. Now, the advantage of this, instead of using TRPO directly, is that it's easier to implement because TRPO is notorious for the second order optimization. But now we are employing the advantage of PPO. And secondly, it is theoretically justified because of the trust region constraint problem that we mentioned earlier. But it is still unbounded because you see, if it is outside of the clipping range, there is no force to drag it back. We will just stop optimizing. We will be staying there, but we will not pull it back, so it's still unbounded. Now that we get to our truly PPO algorithm, which the rollback function is stated as the conditional penalty, which means that it will satisfy a certain condition for it to trigger the penalty function. Now, the penalty function originally in PPO penalty is adding the penalty no matter what value it is. But here, if the KL divergence is greater than a certain delta, and the likelihood ratio for the new policy is times the advantage is greater than the likelihood ratio times the old policy, then we will trigger the penalty function. Otherwise, we can simply minus a constant, and constant does not affect the gradient at all. So here are some details that the rollback function employs conditional penalty and trust region constraint. Conditional penalty and trust region constraint. It determines the step size alpha iteratively, because in the previous page, not previous, but in the original page, that we know that the alpha is hard to determine across different tasks. And third of all, the monotonic improvement is guaranteed. Since the previous two algorithms has been proved, we will not prove it right here, but introduce some experimental results. Here are some experimental results, which we test from 6 different algorithms, which includes PPO, the original one, Truly PPO, PPO rollback, and trust region PPO. And our target, of course, is Truly PPO. And so I'm just going to look at those algorithms with PPO. So we can clearly tell that Truly PPO outperforms other algorithms, since across 6 different tasks, it outperforms other PPO algorithms on 4 different tasks: the hopper, reacher, walker, and half cheetah. And so we can know that PPO rollback, the only PPO rollback and the trust region PPO, may perform very great in some tasks, but thoroughly combining the two is the best solution. So this is my lecture video. Thank you all very much for your attention and staying till the end.